Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we're jumping into the final, and I think most exciting part of Unit 9, Ray Optics.
Optical instruments?
Yes, optical instruments. We're going to see how everything we've learned about reflection and refraction comes together to explain microscopes and telescopes. And our mission is simple, to make this topic so clear that you'll never forget the formulas or the core concepts for your board exams. So let's start with a really basic question. How is it even possible that we use these simple curved pieces of glass lenses to see things that are just worlds apart? I mean, tiny, tiny bacteria on one hand.
And then huge galaxies millions of light years away on the other. It's incredible.
Exactly. How can we manipulate light on such a massive scale, going from something you can't see at all to something that's almost infinitely far?
It does seem like magic, really.
Well, the physics behind it is even more interesting than magic. And a key principle, one we sometimes overlook, is total internal reflection, or TIR. Think about a diamond. Why does it sparkle so much?
Because of the way it's cut?
That's part of it, but it's really about its physics. A diamond has a very high refractive index, about 2.4. And because of that, its critical angle is tiny.
How tiny?
Only about 24.4 degrees.
Oh, wow. So that means light entering the diamond. It gets trapped inside.
Perfectly could. It gets trapped. It hits the internal surfaces at an angle much greater than 24.4 degrees, so it just keeps reflecting internally. It can't escape easily.
So it acts like a perfect mirror on the inside.
A perfect mirror. And this exact same principle, this trapping of light, is what makes modern fiber optic cables work.
The ones that run the internet.
The very same. So the physics that makes a diamond sparkle is the same physics that sends your data across oceans. It's all just geometry and light.
That's a great way to think about it.
Okay, so let's formally define this. Optical instruments are basically tools. They're engineered combinations of lenses and sometimes mirrors.
Right.
Designed to push our vision beyond its natural limits. They help us see the very small or the very, very far away.
So they're basically extensions of our own eyes.
Exactly. And to understand how they achieve such high magnification, let's use an analogy. Think of it like a relay race.
A relay race, okay.
Because no single lens can do the job. You can't get massive magnification with just one piece of glass without all sorts of problems. So light from the object starts the race. It hits the first lens, the objective. That's your first runner.
And it carries the light, which is like the baton?
Precisely. The objective lens takes this light baton and gives it the first magnification, creating an intermediate image. Then it passes this modified baton to the next runner.
Which is the next lens.
Which is the eyepiece.
Yeah.
The final huge magnification is a result of this staged process. Each lens builds on the work of the one before it.
I see. It's a team effort. But why do we even need this? What's wrong with our eyes?
Well, our eyes are amazing, but they have limits, right? There's a near point, D, which is about 25 centimeters. You can't focus on anything closer than that.
And resolution limits, too.
And resolution, yes. Ray optics gives us the blueprint to build tools to overcome these biological limits. I mean, microscopes gave us biology as we know it, cells, bacteria, and telescopes gave us modern astronomy.
He literally opened up new universes.
They did.
Yeah.
Now let's build a clear mental image. Picture a compound microscope.
Yeah.
Light comes up from below, through your sample. It first hits the objective lens. This is our first and very important runner.
And this objective has a short focal length, right?
Very short. That's key. It needs to bend the light strongly to get that first powerful magnification. It creates a real inverted image inside the microscope tube.
Okay, so that's the first handoff of the baton.
That's the first handoff. Now that real image becomes the object for the second lens, the eyepiece.
Ah, the second runner.
The eyepiece takes that already magnified image and magnifies it again, creating a final virtual image that your relaxed eye can see comfortably.
So a two-stage multiplication of power. That makes so much sense now.
Perfect summary. That's the core idea. Now let us see how NSERC formally defines this, especially the maths of it. We call it magnifying power, or $. Could you read the formula for the simple microscope first?
Of course. For a simple microscope with the image at the near point D, the magnification is $1 is 1 plus DFD.
Good. That's our baseline, a single lens magnifier. Now for the compound microscope, our relay race system.
Okay. For a compound microscope with the image at infinity, the total magnification is $1 is mo times me. This is also written as 1 molar as LFO times DFD.
Excellent. Now let's break that down. There's a lot in there. $4 is the objective's focal length. 4 is the eyepieces.
Right, but what is that L tube length?
It is the tube length, but for an exam, you have to be specific. It's the distance between the second focal point of the objective and the first focal point of the eyepiece.
Okay, that's a very precise definition.
It is. A longer tube length, a larger L, actually gives you more initial magnification from the objective.
That makes sense. But my main question is, why are we multiplying dollars and why not just add them?
That is a fantastic question. It's because magnification is a chain reaction. It's multiplicative. Think of it this way.
Okay.
Let's say the objective magnifies the object 10 times. So normal is $10.
Right.
Now, the eyepiece doesn't look at the original object. It looks at the image that is already 10 times bigger.
I see.
And if the eyepiece magnifies that by 5 times, the total effect is 10 times 5. It's 50. You're magnifying the magnified image.
Not just adding the powers, it's a compounding effect.
Precisely. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's quickly look at the telescope formula. It's a bit different. What does insert say for a telescope in normal adjustment?
For a telescope, the magnifying power is $1 is $1.
A ratio.
Yeah.
Not a product. Here, for a telescope, you want a very large focal length for the objective, $5.
To gather as much light as possible from distant stars.
Exactly. And you pair that with an eyepiece that has a very small focal length, $5, to magnify the small image the objective creates.
Okay, wait. I'm a bit confused again. It's still two lenses, an objective and an eyepiece. Why is it a division here and a multiplication for the microscope? It feels like the physics changed.
Excellent point. It highlights a different purpose. With a telescope, we're not trying to make a small thing look linearly bigger. We're concerned with angular magnification.
And the angle it makes at our eye.
Yes, the object is at infinity, so the initial image is tiny. The formula 5 Theta Lowry is really a ratio of the angles, the angle of the final image at your eye versus the angle the distant object makes without the telescope. It's a different way of quantifying the zoom.
Okay, that distinction helps. It's about angles, not just size.
Exactly. Let's do a quick example. A small telescope has an objective with $5 and an eyepiece with $5 exocillocentimeters. What's the magnifying power?
That would be $1 Fife, so 144 divided by 6.
Which gives you?
24. It's magnified 24 times.
Correct. The angular size is 24 times larger. Now, one last thing here. For really big telescopes, using massive lenses is a huge problem. They are heavy, they bend, and they cause something called chromatic aberration.
Where different colors focus at different spots.
Yes, so you get color fringing. To avoid this, big telescopes use mirrors instead of lenses, like the Cassegrain telescope design. It's a reminder that the principles of reflection are just as important as refraction in these instruments. All right, now for the part that can really save you marks. The silent killers. These are the small misconceptions that can trip up even good students.
I'm ready.
Misconception number 1 is about the microscope. The wrong idea is to get super high magnification, you just need one really big, powerful objective lens.
Honestly, that sounds logical. Bigger should be more powerful, no.
That's the intuitive trap.
Yeah.
But it's wrong. The correct idea, and Ensert points this out, is that to get high total magnification, both the objective and the eyepiece must have short focal lengths.
Both of them.
Both. Remember the formula. It's a product. The total magnification dollar is inversely proportional to both $4 and $5. If one of them has a large focal length, it kills your total magnification.
So short focal lengths all the way.
All the way. The memory hook is short focal lengths, big vision.
Okay, I'll remember that. For powerful microscopes, both the objective and the eyepiece must have short focal lengths. It's the only way to get a big product.
You've got it. Now, misconception 2 is about virtual images. It's a bit more philosophical. The wrong idea is a virtual image isn't really there. You can't see it without putting a screen or a piece of paper there.
That's genuinely confusing. We are taught real images can be projected, but virtual ones can't. So how can we see it if it can't be put on a screen?
The confusion is understandable, but the image does exist in terms of the light path. The lens has bent the light rays in such a perfect way that when those diverging rays enter your eye, your brain traces them back to a point in space where they appear to come from. The light is real. The path is real. The location is just an illusion created for your brain.
So my eyes, lens, and retina are acting as the final screen.
Your retina is the screen. You don't need the paper in between. The lens has already done the work of preparing the light for your eye.
That clears it up a lot. The path is real even if the image location is virtual.
Exactly. So our memory hook is virtual image is real light. The path exists even without the paper. Okay, to lock all this in, a few quick memory anchors. For the formulas, just remember this phrase. Telescope equals far over near. Microscope equals multiply the power times me.
That's simple and effective.
And for a physical gesture, you can cup one hand tightly, that's your short focal length objective, and hold it near your eye. Then put your other hand a bit further away for the eyepiece. It reminds you of the two-stage process.
I can picture that.
And finally, just remember the impact. These instruments unlock the universe, from cells to galaxies. Ray optics is why we can see beyond our own biology. So to wrap up, let's do a quick three-point summary for your final revision.
Nice.
Point 1. Optical instruments use lenses and mirrors, following the rules of reflection and refraction, to get past the limits of our eyes, like the near point and resolution. Point 2. For a compound microscope, total power is the product of the objective and eyepiece magnifications. To get high power, both lenses must have short focal lengths.
Got it.
And point 3. Big astronomical telescopes use large mirrors, not just lenses. This is to gather more light, get better resolution, and avoid problems like chromatic aberration and the sheer weight of a giant lens. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes,
Yeah.
ProfSam.com. Thank you for diving deep with us today. All the best for your exams.